Welcome to Real Analysis Basics B4, the Bolzano-Weierstrass Theorem. A bounded sequence may refuse to converge, but it cannot prevent every subsequence from converging. Even chaos has budget constraints. We will prove the theorem twice and then study subsequential limits. Everything will stay in the language of real sequences and intervals. The Bolzano-Weierstrass theorem says that every bounded real sequence has a convergent subsequence. The original sequence need not converge. We only promise that a carefully selected infinite list of its terms does. The proof using B3 is almost offensively short. Every real sequence has a monotone subsequence. A subsequence of a bounded sequence is still bounded, because deleting terms does not destroy the same upper and lower bounds. The monotone convergence theorem now makes that bounded monotone subsequence converge. The theorem is proved. That proof is complete, not a trailer. Still, a second proof shows how repeatedly bisecting an interval forces a convergent subsequence. Consider closed intervals ik, with each interval contained in the previous one, and with lengths tending to 0. The shrinking nested interval lemma says that exactly one real number belongs to every interval. We prove it now. Since unexplained theorem teleportation is not a proof technique. Nestedness makes the left endpoints increasing and the right endpoints decreasing. More importantly, alpha j is at most beta k for every pair of indices j and k. Indeed, if j is at most k, then alpha j is at most alpha k, which is at most beta k. If j is larger than k, then ij lies inside ik, so alpha j is still at most beta k. Thus every beta k is an upper bound for all left endpoints. Completeness therefore gives the finite real number L equal to their supremum. For every k, alpha k is at most L by the definition of supremum. Since beta k is an upper bound for all left endpoints, L is at most beta k. Hence alpha k is at most L and L is at most beta k. So L belongs to ik for every k, proving that the common intersection is non-empty. If L and k both belong to every interval, their distance would be at most the length of every interval. Those lengths tend to 0. So L equals k. The shrinking nested intervals have exactly one common point. This proves the exact nested interval result we need, directly from the least upper bound property. Nothing was smuggled in from a later chapter. Suppose every term lies in a closed interval from a to b. Bisect that interval into two closed halves. At least one half contains infinitely many terms, otherwise both halves would contain only finitely many, and so would their union. Choose such a half as I1. Bisect it, keep a half containing infinitely many terms, and repeat. We obtain nested closed intervals whose lengths are b minus a divided by 2 to the power k. Hence tend to 0. Every ik still contains infinitely many terms by the result just proved. The intervals share a unique point L. Choose n1 so that a n1 lies in I1. After choosing nk, choose a larger index nk plus 1 whose term lies in ik plus 1. This is always possible because each chosen interval contains infinitely many terms. Not merely the same finite collection wearing smaller boxes. Both a, nk and L lie in ik, so their distance is at most the length of ik, which tends to 0. Therefore a nk converges to L. That completes the second proof of Bolzano-Weierstrass. A real number L is a subsequential limit of an if some subsequence converges to L. Some books also call this a cluster point of the sequence. We will use subsequential limit as our main term. Here the two names mean the same thing. Equivalently, For every positive epsilon, infinitely many terms an satisfy absolute value of an minus L less than epsilon. A convergent subsequence clearly gives infinitely many such terms in the other direction. Choose successively later terms within 1 over k of L. -1 to the power n has subsequential limits -1 and 1. 1 over n has only 0. The sequence n has no real subsequential limit, since every subsequence is unbounded. Bolzano-Weierstrass says precisely that a bounded real sequence must have at least one subsequential limit. For a bounded real sequence, convergence to L is equivalent to L being its unique subsequential limit. If an converges to L, every subsequence converges to L, so uniqueness is immediate from B3. Conversely, suppose an does not converge to L. Negating the definition produces some positive epsilon 0 and arbitrarily late terms whose distance from L is at least epsilon 0. Choose those offending terms with strictly increasing indices. We obtain a subsequence that always stays at least epsilon 0 away from L. Because the original sequence is bounded, this offending subsequence is bounded. Bolzano-Weierstrass gives it a convergent subsequence with limit k. Every term of that smaller subsequence stays at least epsilon 0 from L. Taking limits shows that k also stays at least epsilon 0 from L. Thus k is a subsequential limit different from L, contradicting uniqueness. Therefore the original sequence converges to L. Boundedness cannot be deleted. Let the even terms equal 0 and the odd terms grow without bound. 0 is the only real subsequential limit, yet the full sequence diverges. One missing hypothesis. One conveniently false theorem. To summarize, every bounded real sequence has a convergent subsequence. We proved this once using monotone subsequences and once using shrinking nested intervals. For bounded sequences, having exactly one subsequential limit is equivalent to convergence. That is all for B4. Bounded chaos still accumulates somewhere.